Well, welcome back. We're still in 11.3. This video is just one problem. I saw this in a textbook and I thought we'd give it a try. Before I did, I thought I'd practice it, and boy, we need to look at this one. It's pretty crazy. So, we take a look at this guy and we imagine it maybe as perhaps an integral that we are able to handle. Maybe, who knows? And so we decide, let's try the integral test. So that's what this is about. It's an example of the integral test on a crazy problem. So let's write it out first. We're going to run the integral test. And the first thing we're going to do, I'm going to be very official about it. Number one, I'm going to say so I'll just say right over here, let f of x equal natural log of x over x squared. So I'm going to use this guy for the argument all the way to the end. Okay, so first and foremost, and by the way, well, I'll say it over here. So natural log of x over x squared is greater than 0. It's positive, right? And I have a mistake here I'm going to fix actually. I'm going to change n equals 1 to n equals 2 to infinity, because if we plug in a 1 in the first case there, we get 0. So who needs that there? So I had to switch that and say on the interval x in 2 to infinity. You notice if I put in a 1, ln of 1 is 0, so let's start at 2 instead. So step number 1, I'm verifying the hypothesis. Yes, it's positive. 2, we'll take the limit as x goes to infinity of the function. And watch what happens here. This thing goes to, it goes to infinity over infinity, which means we are in L'Hopital world. Yep, I'm going to run it. So it's equal to, by L'Hopital, the lem, as x approaches infinity. And we'll take the derivative upstairs, thank you very much, and the derivative downstairs. If I invert and multiply, I get lem, as x approaches infinity, 1 over 2x squared. And as we all know from Calc 1, if the denominator grows without bound, we go to 0. So step number 2, the terms go to 0. That's all well and good. Wonderful. Okay. We got to go to step 3, which shows that it's also decreasing. We may wonder why that's a thing, but we do it just the same. 3, is it decreasing? So for decreasing, we get to wander into the first derivative test. Remember that guy? It's where you take the derivative and you look at the sign of the derivative. So we're going to take f prime, thank you. And this time it's not L'Hopital. This is a quotient rule problem. So I'm looking at the function up there, okay, and I'm squaring the denominator and bringing it up. Multiply with the derivative upstairs. Natural log is 1 over x minus the natural log of x times the derivative downstairs, which is 2x. So we're getting, I'm going to see there's an x here. I'm going to pull out an x that's going to leave a 1 minus, I think, 2 natural log of x all over x to the 4th. I'll reduce the x's also and end up with 1 minus 2 natural log of x all over x cubed. And our game is, when is that equal to 0 and when do the signs change? I want to verify that the derivative is, well, I need it to be decreasing. So I want to show that the first derivative is negative. That's what we're doing. We're taking the first derivative. Now you see why we're doing that? Okay. Well, when I set 1 minus 2 ln x, the numerator, equal to 0, I get ln x, a little bit of 1 over 2. So that means x is the square root, really, of e to the 1/2 power, which is about 1.6. Now remember, our number line, I decided not to start at 0 or at 1 because the first term is 0. So here's 0. You notice in the derivative it's undefined there, right? And here is 2. That's where we're starting. And here's 1.6 where the sign possibly changes. So you understand, It's really here where I'm interested in the sign of the function. If you plug in a number, like say for instance x is equal to 3, if you plug it into this guy, you get 1 minus 2 ln 3 all over 3 cubed. You know what? That is negative. You can do it on your own. And what we've proven is the function finally is decreasing. Yay! So this particular series satisfies the integral test. You think you're done. You're not. You got to run the test now. And that means what we do is we actually integrate from 2 to infinity this particular guy, the natural log of x all over x squared dx. Okay. That looks pretty crazy. Let's help each other out. The u substitution here I would use is, let's try that natural log guy. U equals natural log because du is 1 over x dx, but we have an extra x, don't we? Let me write out what we've got. It's the integral from 2 to infinity. We've got the natural log of x. We have a couple of 1 over x's, if you will, and I'm just showing you what we have. So what we have substituted thus far is this guy is u, and all of this is du. But we have this lone guy in the middle. What can we say about it? Well, look at this guy. It's fancy. If u equals the natural log of x, then x itself is e to the u. So this is actually 1 over e to the u. It's 1 over e to the u, because that's what x is equal to. I told you it was a doozy. Here we go. So our new integral looks like this. It's the integral of u e to the minus u du. U e to the minus u du. I saw this, I go, no, they don't want me to do this. But you know what? This is a great one for a teacher to show, and a great one for an author to put in the book, because we have to now do what kind of method on this guy? We've seen these before. This is where you have to go, let w equal u, so dw is du. Yes, I'm doing by parts. Oh my goodness, I did L'Hopital, now it's by parts. So dv is e to the minus u du. So v upon integration, little tiny u substitution on that, is minus e to the minus u. All right, so you're going to have to verify that. Maybe pause and verify it. So the integral now becomes uv, or not uv, wv, these two guys. Okay, so you're getting minus u e to the minus u minus the integral of v du, which is another minus, so I'll just write it as plus e to the minus u du. We're almost there. So we're getting minus u e to the minus u minus e to the minus u. Okay, I'm going to write it a different way. I'm going to write this as, I'm going to factor out a negative in front. I'm going to send e to the u downstairs because it's in both terms. And here we'll have u plus 1. Pretty fancy, but it's still u. I'm going to switch back to x. So minus ln x plus 1 over e to the ln x, which, well, hey, look at that. Minus ln x plus 1 over x, finally. And now what I want to do is run the limits from 2 to infinity on this thing, okay? This has got to end here shortly. So we get a minus natural log of infinity plus 1 all over infinity. That looks not promising. Minus a minus is plus, and we have the natural log of 2 plus 1 over 2. The trouble is, as always, there. We got to take this limit. You know what I have to do is I have to go back to L'Hopital again, because if I look at this limit, it goes to minus infinity over infinity again. So I'm going to write by L'Hopital, believe it or not, this is how this is done. This is the lim as, say, b goes to infinity of minus, and now I'm going to, well, let me write it out first. Natural log of, well, you know I won't. I'll do L'Hopital using this model right there. Okay, so it'll be minus 1 over x over 1. Over here we have this ln 2 plus 1 over 2. But this guy, as b goes to infinity, Oh boy, I should have said x. What was I thinking? X goes to infinity, and we put the x there. And as it does so, what do we get? He goes to 0 finally. And so our answer after all this work is that the integral from 2 to infinity of the natural log of x all over x squared dx turns out to be convergent. It's the natural log of 2 plus 1 over 2. What we care about is that it converges. So that implies that the series n equals 2, he comes back again, natural log of n over n squared also converges. Now, they're not all like that, but that was a doozy, and I thought I'd share it with you. Don't say we never gave you nothing. So, yeah, the rest of them, figure out how to integrate them. This one I saw, I think, in your textbook and in another, and it is quite something, isn't it? It's really putting us through our paces as far as calculus is concerned. And that should be enough, I think, at least for the online videos for the integral test. So enjoy the homework.